All right, another topic that we've looked at is differentiability. A little bit of a tongue twister. So a function is said to be differentiable at a point if the derivative exists. Seems nice, simple, innocuous, and it's not that bad when you have the graph in front of you, but there is definitely some calculus work that needs to be done. So the formal definition reads, a function is said to be differentiable at x equals a if the derivative exists at x equals a. That's all that it means. The derivative exists. But since a derivative involves limits, as we've seen, the limit as if I want to find the derivative, the limit as x approaches a, we do f of x minus f of a over x minus a. If this exists, what we're really saying is that the limit as x approaches a from the left and the limit as x approaches a from the right of the derivative, they have to be the same. If they are not equal, then the derivative doesn't exist, which means the function is not differentiable. We can talk about differentiability at a point. We can talk about differentiability on an interval, like from a starting value to an ending value. We can even talk about a function being differentiable everywhere. So that's differentiability. The derivative has to exist. So let's go through a quick checklist on how you actually decide if a function is differentiable at a point. Now this is assuming that you have the graph in front of you. So first of all, your function has to be continuous. If the function is not continuous, if you have a hole, if you have a jump, if you have a break, if you have a vertical asymptote, then the function will not be differentiable. So I look at this function over here, and right away I am drawn to x equals 0. I have a point down here. I have a hole up here. The function is not continuous at x equals 0, and since it's not continuous at x equals 0, then automatically that means it's not differentiable at x equals 0. So the first thing we're always going to check for, continuity. The second thing that we're going to look for are sharp turns or cusp points. And we've made a big joke out of the word cusp point because it sounds like you're spitting, it's very harsh. We want a smooth function. If I were to take the derivative for this function over here, I see that the derivative is going to be positive. The slope of the tangent line is increasing. I'm sorry, the slope of the tangent line is positive. Over here, my function is decreasing. The slope of the tangent line is negative. As I get closer to this point over here, I have a derivative on the left is positive, the derivative on the right is negative. Those are not equal to each other. So that cusp point means, again, not differentiable. And it's not differentiable because the derivative from the left and the derivative from the right are not equal. The last thing so that's the second thing. The last thing we're going to check for in terms of differentiability is, do we have a vertical tangent? What I mean is, when I draw in a tangent line to the graph, for example, this one, if the tangent line is vertical, then we would say that the function also fails to be differentiable. Okay, I see a cusp point over here. We already know that fails to be differentiable. But right over here at -1, it's subtle, it's hard to see. But if you were to draw in a tangent line there, you have a vertical tangent. With a vertical tangent, what that means is the function is not differentiable. Okay? So to summarize, if I want to determine whether a function, if I have the graph in front of me, if I want to know if it's differentiable at a point, I first check for continuity. If the function is continuous, move on. Second, I look for sharp points. If there are any sharp points, then it won't be differentiable. If I have a continuous function, if I have no cusp points, but I have a vertical tangent line, the function also fails to be differentiable. So those are the three things that you check. Now, let's actually talk about how we can prove something like this, because that is always the million-dollar question in AP Calculus. So, question A. or part A, we have this function, again a piecewise function, love those piecewise functions. I want to determine the value of b, which will make f continuous at x equals 2. Well, what we've learned so far is that if I want to establish continuity, I have to first show that f of 2 is defined. Can I plug 2 into my function and get a real number? Sure. According to my domain restriction, if x is greater than or equal to 2, I use the bottom function. I get 2 times the square root of 2 minus 1. That is 2 times the square root of 1 is 2. Is that defined? Yes, it's defined. Second, we need to find the limit as x approaches 2 from the left of f of x. The limit as x approaches 2 from the left, those are numbers less than 2, is going to be negative 4 times 2 squared plus b times 2. That's negative 16 plus 2b. I need for the limit on the left and the limit on the right to be equal to each other. When I find the limit on the right, well, we've already gone through that before, we get 2. If the function is going to be continuous, then it must be true that the limit on the left and the limit on the right are equal to each other. So I set them equal to each other. I solve that equation. I get that 2b equals 18, so b equals 9. What's so special about b equal to 9? If b is equal to 9, then the expression on the left, which is your limit as x approaches 2 from the left, is equal to the expression on the right, the limit as x approaches 2 on the right, and that would tell me that the limit as x approaches 2 of f of x is equal to 2. In order to wrap up continuity, we need to state that the limit as x approaches 2 of f of x is equal to f of 2. Those are indeed equal to each other. Therefore, f is continuous at x equals 2. Done. That's part A. That had nothing to do with differentiability. That had everything to do with continuity. Let's look at the question in part B. In part B, for the value that we found in part A, what did we decide? B is 9. So for b equal to 9, is f of x differentiable at x equals 2? Well, in order to do that, I need to first know, is the function continuous? Sure, we know it's continuous at x equals 2. That's how we selected this value of b. We've already shown that work. What we need to do is we need to show that the derivative exists. So in order to do that, I have to first find the limit as x approaches 2 from the left of the derivative. So we need f of x minus f of 2 over x minus 2. That is, limit as x approaches 2. For numbers less than 2, my function is negative 4x squared plus 9x. Remember, we figured out that b was 9. Minus f of 2. When I plug 2 into the function, we get 2 over x minus 2. Let's keep going. Limit as x approaches 2 from the left, negative 4x squared plus 9x minus 2 over x minus 2. Well, we're going to have to do some algebra. I can factor out the negative, and that'll leave me 4x squared minus 9x plus 2. In the denominator, x minus 2. That's limit x approaches 2 from the left, negative 1. Most of us have gotten pretty good with this whole limit process, and you know that when you get 0 over 0, what that means is you have a common factor. So we need x minus 2 to be a factor of the numerator. That'll happen if the other factor is 4x minus 1, and everything works out nicely. X minus 2 cancels out. The limit as x approaches negative as x approaches 2 from the left, negative 1 parentheses 4 times 2 minus 1, negative 7. So we can conclude that the limit as x approaches 2 from the left of f prime of x equals negative 7. Now let's be careful. This in and of itself doesn't show me f prime of 2 exists. We have to go further. We need to also check the derivative from the right. So we're going to find the limit as x approaches 2 from the right. Okay, well, let's see. 2 from the right means we're going to use 2 square roots of x minus 1 as f of x. 2 square roots x minus 1 minus f of 2 is 2 over x minus 2 again. If you were to evaluate this limit at 2, you're going to get 0 over 0. We need to do some algebra trickery. That algebra trickery is going to be in the form of the conjugate again. So let's do it. Multiply 2 square roots x minus 1 plus 2. Denominator 2 square roots x minus 1 plus 2. Multiply your numerators. Limit x approaches 2. 2 square roots of x minus 1 times 2 square roots of x minus 1 is 4 times x minus 1. First term with the last term cancels out with the last term multiplied with the first term over here. Minus 4. In the denominator, x minus 2, 2 square roots x minus 1 plus 2. We get limit x approaches 2. 4x minus 4 is the same as 4x minus 8. Some of you probably already see what's going to happen next. That 4x minus 8, I can factor out of 4. There's that factor of x minus 2 that we knew had to show up somewhere. There it is. X minus 2 cancels out. We get limit x approaches 2 from the right. Oh my goodness, I stopped writing x approaching 2 from the right. 4 over 2 square roots x minus 1 plus 2. Take the limit as x approaches 2. Numerator stays 4. Denominator 2 times the square root of 1 plus 2. We get 4 over 4, which is 1. So the limit as x approaches 2 from the right of f prime of x is 1. But the limit as x approaches 2 from the left is negative 7. Since these two expressions are not equal to each other, our conclusion would be, therefore, f prime of 2 does not exist. If the derivative doesn't exist, then we get to say f is not differentiable. Differentiable at x equals 2. We showed in part A that the function is continuous at 2, but sadly it's not differentiable at x equals 2. We're expecting some sort of a cusp point, some sort of a sharp turn. So again, if you can do this problem, you are prepared for excellence on the unit test and anything that is going to come your way. Most important thing is when we're showing differentiability, you first need to establish continuity. So show the function is defined, show the limit from the left and the limit from the right are equal to each other, show that the limit is actually the same as the value of the function at that point. Therefore, we've concluded the function is continuous. Now, we go after the derivative on the left and the derivative on the right. If these had been equal, then we would be able to say the function is differentiable. Since they weren't, it's not differentiable. Done. High five your neighbor. We are done with that video.